Everyone, and welcome to Chase Plastics Chase the Knowledge webinar on Introduction to Plastic Additives. My name is Sherry Cudd, and I'm the Advertising and Marketing Manager for Chase Plastics. Thank you all for your interest in this webinar and for taking time out of your day to attend. I do have a few quick housekeeping items before we begin. If you are watching us on YouTube, we encourage you to like and subscribe so you receive future notifications when Chase the Knowledge webinar recordings are posted. As for those of you who are listening live, everyone except the presenter is on mute and will be for the duration of the webinar. But if you'd like to ask a question, you can do so at any time by typing it in the questions section of your toolbar. If you'd rather ask verbally, please raise your hand using the react icon in the toolbar, and I will unmute you and call on you to ask your question out loud. We will answer all questions at the end of the webinar, so stay tuned. You can access and download PDF copies of this presentation, our product line card, our one-pager on polymer modification, and information on our technical engineering team in the materials section during this presentation. If you are attending live, a certificate of completion and recording of the webinar will be emailed to you about an hour after the webinar concludes. You will receive a separate email from Andrea with a PDF presentation and the handouts. We would greatly appreciate it if you could complete the survey at the end so we can improve future webinars for you and cover the topics that interest you most. We encourage you to check out past webinars and recordings on the webinars page of our website at chaseplastics.com/webinars. If you would like a custom Chase the Knowledge presentation given to your organization discussing a specific topic or material, please send an email to your presenter, Andrea Kendrick, or myself. Our entire sales and technical team are always ready to assist with technical issues, material selection, and educating you and your team on products and processes specific to your needs. Future Chase the Knowledge webinar announcements will also appear on this page as they are posted. Our next webinar will cover navigating CPS Connect from our website to access your account. More details to come on that, but it will happen mid to late March of 2026. You can also subscribe or invite your coworkers to subscribe to receive notifications of all future Chase the Knowledge webinars. As I mentioned, we are also on YouTube. Just search for Chase Plastics on YouTube to find our channel where all our Chase the Knowledge webinars are and will be posted for easy viewing. Hit subscribe to be notified through YouTube when we post new content. Another great technical resource is the Chase the Knowledge blogs on our website. They can be found at chaseplastics.com/blogs or under the resources tab from the homepage. And you can see that we have a current or a new blog on there on the advantages of siloxane for process improvement and surface modification. In addition to our presenter, Andrea Kendrick, whom I will introduce in a moment, we also have Jason Merkel, Technical Manager, on hand to answer your questions today. At this point, I'd like to hand it over to our presenter, Andrea Kendrick. Andrea is a technical training engineer with Chase Plastics and has been with us since 2015. She received her bachelor's degree in plastics engineering technology from Ferris State University. For those of you who have attended Chase the Knowledge webinars in the past or contacted our technical engineering team for assistance, you're very familiar with Andrea and the level of expertise that she brings to the table. Without further ado, Andrea.
Hey, good afternoon, everybody. This is Andrea Kendrick, and today we're going to go over plastic additives. So our agenda for today, we're going to cover a handful of different additives, and then we're going to potentially in future ones cover even more additives, because as I was putting this together and filling it up with information on these additives, I was finding we could have easily done a single presentation on any number of these different additives and fill an entire presentation of 20, 30 slides on each. And I didn't want to have an extremely long presentation, so we're going to split this into two. So we'll do these additives this time, and the next time we get together for additives, I'll cover other ones like flame retardants and heat stabilizers, UV stabilizers, stuff like that. So today though, we're going to cover colorants. So we're going to talk about color a little bit. We're going to go over anti-stats and ESD. We're going to go over antimicrobials. We're talk about slip agents, specifically focused on siloxane or silicone slip agents. We're going to talk about nucleating agents, and then we're going to round it off with chemical foaming agents. And then at the very end, I also have a slide going over some considerations or things to think about when we're going to be adding additives to our base polymers. So starting with colorants. Colorants are going to be any substance, generally a pigment or dye, that's added to a plastic to change or enhance its color. And so we might use that for marketing purposes or messaging. So think marketing purpose, think of your favorite brand of anything. It's likely that their logo has a particular color or their products are particular colors that you could easily pick out. And so marketing purposes, messaging, it might also be used to aid in the functionality of the part itself. So if you make similar parts and you make one that's slightly bigger or slightly smaller, maybe you use a color to differentiate quickly which one's which. And so that's used pretty commonly too, why we might use certain colors. The other thing that we would use for colors or, coloring our parts, there's different meanings and associations with them. So for example, yellow, it captures our human eye attention more than any other color. And so when you think of high visibility colors, you think of that safety yellow or that kind of yellow-green color. It's because it grabs our attention more readily than any other color. So that's why we use that very high vis yellow-green color. Red is the international color for stop. Green is the most diverse color. There's the most color options of green. It's also used for exit signs in areas where you might have smoke or fire nearby because it is the most visible. So again, it could be any number of reasons we use a certain color, maybe because of how we see it or attribute it, or marketing purposes for logos or products. Color in general comes in different forms. So it might come in a powdered form, it might come in a pellet form, which is going to be the most common, at least for us, and then liquid form. And so pellets would be, you could receive either universal color. So if you've heard the term a universal color, generally they're referring to a color that's in an EVA or some form of a polyethylene base that can be used for a wide range of different resins. Now those resins though are going to be limited to ones that can withstand certain temperatures. And so because of that EVA base, that polyethylene base, and the heat performance of the pigments or dyes in those materials, it's going to limit what it can go into. So generally from a thermal standpoint, right around the nylon 6,6 polycarbonate processing range, so you're kind of mid 500s plus, is where we start to kind of draw the line, where we're going to have to start looking at utilizing a resin specific colorant because we're going to start being a little too hot. And then also at that temperature, some of the pigments to be used start to have limitations. So if you think of very vibrant colors, neon colors, yellows, those can be difficult to do in higher temperature materials because of a limitation on the thermal performance of that pigment. Okay. So now let's go into just briefly the different forms of pigments that we might use here. And so you could use an inorganic pigment. These are generally complexes of metal. So these are going to give you your better heat performance and better light fastness. So better for kind of like a UV exposure type thing, but they're not going to be as vibrant. So if you're wanting that really neon color, you're really not going to get that with inorganic pigments. So some examples of those are going to be iron oxides, cobalt blue, and cadmium yellow. And so those are going to be kind of your metal oxide versions of pigments that might be used in colorants. Organic pigments, which are going to be a little more common, they're going to be a little bit brighter, more vibrant, greater color strength, but they are going to be more sensitive to heat and light. So again, limitations on processing temperatures for some of these pigments if we're trying to use them in higher temperature materials. So stuff like your PPAs, your PEIs, those are going to be all too high temperature for some of these standard pigments. And then the organic ones are based off of synthesized organic molecules. So some forms of oxygen, hydrogen synthesized to make these different colors. And then lastly, so those are our pigments. So those are going to be used in your universal or resin specific colorants. Then lastly, we have dyes. Dyes are also going to be organic, but what they don't have is they don't have visible particles. And so they are utilized in transparent materials. So when you think of a polycarbonate or a sulfone and it's got that smoke tint to it, what they would do is utilize a dye to create that. Or something like the acrylic in a rear lens on a car that's red, a dye would be utilized there because the pigments get in the way. It would block the light. You would no longer have a transparent material. But the idea is we want it to be transparent. We just want a transparent color. So we would utilize a dye to do that. So some examples of some colors you might see. Some of these you can see and look at them and tell me exactly the company that they're related to, specifically the two middle pictures, without me saying anything. So we are able to associate that color specifically with that company without anything having to be said. Colors are used heavily in toys, Legos, used for housings on chainsaws for another common company that you might see there, or a hedge trimmer that you can see in the bottom left, high vis colors. So again, a lot of different reasons or places we would utilize different colors for our products. So we want to make sure we're matching those colors. Some other places would be automotive colors. Each big end user has their own variants of different colors that you might be asked to do. Piano black, ebony black, bunch of different colors that you might be asked to match. And so we would utilize colorants or a pre-colored compound that has those pigments already in to achieve those colors. Okay, so then after we talk about color, why we use it, some of the pigments that are used for it, we have to then understand a little bit about reading it. So I'm not going to go too deep into this, but I do want to touch on it because it is important to understand that this is kind of how you're going to see this information, this color data presented to you when we're talking different colors for different materials. So let's say we go and you have a product you're trying to make, you want to meet a very specific blue. What you'll do ideally is have a part, even more ideal is if it's in a plastic part that can then be color matched. So if you've ever gone through the process of color matching material, you'll send in a part for whoever is going to be making that compound. They'll take a reading of the color and then they will formulate their color and pigments to match that. So what happens is when they take that reading, they map it out in what's called the CIE LAB color space. And so the color space produces coordinates in an area where you can distinguish that particular color meets these different LAB coordinates. And that is specialized for that particular material. So the LAB color space is modeled after a theory that no two colors can both be red and green, blue and yellow, light and dark. And so it maps it out on that space. So when we talk LAB, L is going to be your lightness. And so if you have a color that gets red and the coordinate for the L is a 0, it is a black color. If it is 100, it is a white color. And a lot of times it falls kind of somewhere in between. Then your A value is giving you the difference between red and green. And so if it's a negative value, it's a green. If it's a positive A value, it's red. And then the same for B, but B references blue and yellow. So a negative value is a more blue product and a positive B is a more yellow product. The other thing to note here is there are other color spaces that exist that can be utilized. We just tend to most commonly use the LAB space, and that's what you're going to see most commonly on either certs or on documentation when a color match is being done. This just happens to be the most commonly used one for plastics. There are, of course, other ones, again, as I mentioned, but we use LAB most commonly. Okay. So we talked about LAB, we talked about the different coordinates on that. How do we then compare a lot of a material to the target or standard that has been selected? So again, you send the part in, you're getting it color matched. Now what happens is they find those coordinates for that particular one. In this case, as an example, you can see that there is some polycarbonate. One's a blue edge tint and one is a clear. And you see the blue edge tint has a slightly larger value larger negative value for the B space, making it more blue than our clear does. And so that's where the blue edge tint comes from. It's more blue. It's further down on the negative B value for blue. So those are the coordinates for polycarbonate, blue edge tint, and water clear. And so again, LAB. But now what we do is those would be our target values. So when we compare something, we make a new lot, we make our first lot to make sample chips for you to look at, what have you. What they do is, if you've heard the term delta E or change E is going to be the total difference of color. So instead of just giving you the target LAB values and then giving you the LAB value coordinates of what the part tested at when it had been checked for color, they'll give you a delta E. And what that does is it takes a comparison of all of the differences. So it takes into account the difference in the L space, the A space, and the B space, and then compares it. And so what happens is generally you'll get a delta E value of, wherever it ends up being, and that's comparing our total shift. The other thing to note here as a side note that I want to point out is when a part is sent in for color matching, what ends up happening is whoever is making that color, they'll send sample chips for you to review. If agreed upon, yes, this is it, this is what we want, that sample chip that had been sent is the target now. So whatever coordinates it comes out as for LAB on that sample chip, that's the target now. So every time a lot of material is made, it is being compared to that target sample. And so depending on requirements that you may have, delta E values go from 1 to 100, or less, I should say 0, actually, 0 to 100. Within certain markets where it's really important that the color stays very consistent, you'll see that typically a less than 1 delta E value is specified. And so the reason for that is that you can't detect it. If it's less than a 1, if you put your sample chip and the chip that they make of the new lot of material to compare, if it has a delta E of 0.9, 0.8, whatever it is, as long as it's under 1, your human eye cannot look at the two chips and distinguish a difference between them. And so you have to map it on coordinates, LAB values, and compare that way because you can't see the difference. And then it goes all the way, delta E goes all the way to 100, where you have a completely opposite color. And so depending on the end user specification or your specification, you might lock down a max delta E value for your color differences. And so an example of that would be here. And so in cases where color is important and it had been matched and we have to hit a certain color standard, what you might find is on the certification of analysis, C of A, that you receive with all of your lots of material to go over the testing that was done for that lot to show how it performs, you might find the color standard testing on it. In this particular case, this is a reprocessed material that's black, and you can see the color standard delta E, the specification or the max range for this particular one that's allowed is 1.5. And so a little bit over the 1. So you might be able to, if you have the target and then you get all the way to a 1.5, you might be able to see a slight difference because it is over that 1. But you can see on a cert, this is what it looks like. Delta E value is reported after being tested on here to compare. And so great way to show our color difference here. Again, as mentioned, some end users, automotive tends to stick with a 1 delta E max. So they want to make sure that you can't visually see a difference. If you're going to spend a ton of money on a nice new vehicle, you don't want to be able to look around and see that the colors don't match. You want to see everything that's matching. And the other thing that's nice about delta E, which we'll likely talk about, if we do UV additives and stuff, is a delta E or color shift can also be utilized when we're doing different testing. So stuff like UV exposure, a lot of times a delta E value will be used after a UV exposure to determine how much discoloration the material went through. So delta E is good for holding a standard or determining how different from the starting color it is, but it can also be utilized in other areas where we might do retention, UV exposure, heat exposure type study, and it can be used there as well. So it's not just for color matching, it can also be utilized for other tests as well. All right, so that's color. Again, color is very, there's a lot that goes into color. We can spend a lot of time on color. So if you have additional questions, please feel free to let me know, but I didn't want to have the entire presentation taken up solely on color. So we'll move on to our next one. So now we're going to talk about anti-stats a little bit. So the reason we might utilize an anti-stat is that static electricity will build up on the surface of a plastic part. Plastic materials in general are both electrically and thermally insulative, meaning they don't move the current and don't move the heat. And so not very well anyway, I should say. They moved a little bit, but not by much. And so what will happen is if static is allowed to start to build on the surface of your plastic product, it's going to stay there until it's given somewhere to go. And normally where it's given to go is someone touching it. And then you get shocked because the static had built up and sat on that surface. And so other things that can happen is if you build up static, it can also build up dust and dirt that will collect on it. So you can see in the picture, it's collecting pieces of paper, but it can also collect dirt or dust. And so in certain applications where maybe we need to be able to see through it, maybe it's a lens, maybe it's, you know, for whatever reason, we can't have that dirt and dust build up on it. And so we don't want that. The other thing that could happen too is if you're making large products like totes and you've got that static buildup on the surface of it, it's going to want to stick to other ones. So if you're selling totes and you make a whole bunch of them and you stack them in, they're going to want to stick to each other. It can be hard to get out. So anti-stat makes it, and so they don't want to build up that charge. Okay. So now we kind of know what we need, maybe an anti-stat additive. How do we measure that, or what are we looking at when we're talking about that for a particular material? So the measurement of resistivity is what's utilized for our materials. And on the next slide, I'll go through the different range of ESD materials as well. But we measure the resistivity, which is a material's resistance to moving a current. So because it's a resistance, and we know that our plastic material is insulative, those values are going to be really high. So standard materials are greater than 10 to the 12th ohms range. And so they're all somewhere in that range between 12 and 16 is pretty common for basically every one of our unmodified standard plastics to end up in. To compare that though, something like a metal, they're in less than 10 to the 6th ohms range. So they're very conductive. They move the current quite easily, whereas our plastics do not. So for anti-stat specifically, the additives will help move our plastic material into the 10 to the 9th to 10 to the 12th range. And so in that range, what's happening is that we're stopping the initial electrostatic charges from building up. So they're not able to build up on the surface and sit there and wait to discharge in a spark on someone that touches it. Okay. Some additional ones. All I talk about specifically in this presentation is anti-stat. However, there are other additives that can be utilized to make a material static dissipative and conductive. And so those ranges, excuse me, are going to be in the lower resistivity range, closer to the performance of metal. And so static dissipative, if we moved into that range, 10 to the 6th to 10 to the 9th, you're going to have limited or no initial charges. You're going to prevent the discharge to human contact because it's going to slowly ground that charge. So instead of sitting on the surface, it's going to move it through it out of the way. So when you touch it, you're not going to get zapped and could be quite aggressively zapped depending on how much is being built up. It could be very painful. And then lastly would be your conductive range. So this is performing more like a metal, so less than 10 to the 6th. And so it's going to provide a path and it's going to ground the charge very quickly to another conductive object. So what happens is we'll get asked for a material that's ESD, which stands for electrostatic discharge. And generally it's ESD protection. So protecting electronics, protecting the part, whatever it may be. If you come to us and you say, hey, I need an ESD material, because ESD is referencing those 3 different categories and 3 different ranges, we will need more information on which level of protection is required. So anti-static or anti-stat, which is the additives we're kind of talking about right now specifically, is going to put you in that 10 to the 9th to 10 to the 12th range. So just that initial little buildup will be suppressed. And then if we need to go really much more conductive, static dissipative, or conductive range, we have to utilize something outside of an anti-stat additive. In those cases, you'd have to use stuff like a metal, so a stainless steel or a carbon fiber to achieve those ranges. And so outside of the additive specifically, but it's all stuff that can be done and can be added to make our materials perform the way that they need to be performing. Okay. All right, next additive, just one page on this one, but thought it might be bearing some mention because of with stuff that has gone on in the past. Antimicrobials. So the use here is going to be microorganisms, bacteria, fungi. They're present. We can't see them, but they are present, and they can rapidly grow on plastics. Some plastics are inherently better with antimicrobial resistance or antimicrobial growth, so it stops some of the growth. Stuff like a polyether TPU would have some inherent antimicrobial properties, but you can then add an antimicrobial additive to improve that performance. And so these additives exist in these pictures here off to your left side. Those are polycarbonates that have the additive. So you are, in some cases, able to maintain clarity. So in this case, polycarbonate is still clear and it has the additive there. So maybe a high touch surface that you want or a housing that you still want to be able to see through can be made with polycarbonate with an antimicrobial. So some standard applications, there's gonna be a lot of stuff that requires really good hygiene. And so stuff that you don't want anything to grow in. So your athletic gear, your kitchenware, stuff in the bathroom where it might meet in a moist environment that's gonna be more likely to help the microorganism grow. And so your sweaty gym stuff, your kitchenware and your bathroom stuff might be all good places to put an antimicrobial additive to stop that growth. There are two types that are common. Your first one is going to be your migratory organic substances. And so what will migrate out, these are less likely or harder to get FDA versions. So if you need an FDA compliant one, maybe it's a kitchenware application because it's migratory and it moves, a little harder to do FDA with that. And then a little bit more common option is our inorganic variant, which is going to be based on a silver ion. And so there's other ones. There are some even more aggressive ones that are out there that have been used in the past, but they're slowly being used less and less just because of regulatory stuff. And so slowly they're moving away from other ones that exist, but your organic migratory ones and your silver ion based ones are going to be your most common ones here. Okay. All right, so now we're going to get into slip agents. We're going to get into siloxane, silicone. If you've worked with or heard of slip agents, silicone-based lubricants, you hear a lot of different terms. You'll hear siloxane, you might hear silicone, you might hear, in this case, if you're getting really crazy, polydimethyl siloxane, which is PDMS, which is the actual silicone molecule that's being used. But I want to clear up some of the verbiage, and so that way we kind of understand where we're at with these siloxane-based, silicone-based slip additives. So silicone itself is going to be a polymer. So when we talk polymers, we're talking standard materials like a nylon would be a polymer. Your polypropylene is a polymer. So it's going to be a polymer that contains silicon, which is the element, and then oxygen, hydrogen, and carbon. Siloxane is going to be that functional group between the silicone and the oxygen, or silicon, excuse me, and the oxygen. So a lot of times, instead of calling it a silicone polymer or PDMS, they'll just call it siloxane, which is just calling out that functional group that's in the silicone polymer. And then lastly, if you get real crazy and you dive really deep into it, you might hear polydimethyl siloxane. That's the actual version of the silicone that's being used as a slip agent in most cases. The other thing that's nice about it is you can also functionalize it by giving it different groups off the backbone to get it to perform differently. And so there's different variants of it to get to perform differently for you or have a certain function that's in addition to what it's achieving. So siloxane is an okay term to use. Silicone is an okay term to use. And PDMS is also an okay term to use. But I just want to clear up where all those terms come from. So if you hear them, you kind of understand what we're talking about. Okay, so why would you use a siloxane or silicone-based slip agent? And so it's going to do stuff like help process improvement. So we're going to lower some torques and pressures. It's going to slip a little easier. You're going to have less pressures and torques that are being used. You're going to limit or start to reduce your melt fracturing, which is what you can kind of see in the picture down here on the left. You can see no lubricant here, a little bit of a different based lubricant that's not silicone based, and then your silicone based. So you can see this is the surface of an extrudate coming out of the extruder. You see it's kind of breaking up a little bit. It's not holding itself together super well versus using the siloxane, much less melt fracturing happening, a much more smoother surface that's coming out of your extruder. Okay. You can also help with flow length because it's going to flow a little easier. It helps with mold release. So if you're having issues with releasing from the mold, it can help with that as well. And then when you get enough or add enough in, you can start to affect the actual application itself. So not just process the application. Once you add enough in, because it will get to the surface, and we'll kind of show that in a couple slides, you're going to reduce the coefficient of friction. And so if you're using it in wear applications, maybe it's a gear, maybe it's something that's wearing up against a metal shaft, whatever it may be, if there's moving parts, this can improve your COF, lower it, so it wears a little easier, produces less frictional heat, and has a longer life cycle for the part itself. It improves your abrasion and scratch and mar resistance for most materials. So something like if you've got, maybe your dash in a car or the side door and it's prone to getting scratched, maybe it's a talc-filled propylene or something like that and it's prone to scratching, something like a siloxane or slip agent in there could help improve where it's not going to scratch as easily. The other nice thing is, again, you add enough in it, it gives you a softer or silkier feel. So maybe that's something that you want out of your part. It can do that if you add some of it in. And then lastly, just points to be made is that it's not migratory. So I think a lot of people tend to think it migrates a lot. It's already at the surface. It doesn't migrate after you process it. So once it's solidified, it stays there. And so that's convenient because it allows for use in stuff like food contact. So again, when we talked about your antimicrobial that was migratory, there's issues with it being used in FDA because it will continue to come off of the material. This doesn't do that. So it can, certain grades can be used for food contact. And then little to no effect on additional stuff, odor, fogging, a limited effect on certain things like printing or overmolding, where in past or with other lubricants, you might have a much bigger issue when you try to do that. Okay, some additional properties on it. We talk about the refractive index. This goes for any of our additives. Not just siloxane, not just PDMS. This goes for any of our additives. So this bears mentioning. When we talk about adding anything to a material that is clear, if you do not have the same refractive index as that clear polymer, what's going to happen is you're going to have the light refracting in different areas or different ways than the base polymer, and you're going to likely end up with a material that is no longer clear. So you're going to affect the clarity. So if you've ever ran a polycarbonate and then you purged it out with a polystyrene, or you used a polycarbonate and you added an additive to it and you found that it starts to make the material cloudy, those two different materials that are combining have different refractive indices. And so you're going to end up with a cloudy material now instead of a material that maintains clarity. So it's not as easy as just, oh, if it's clear and I have another material that's clear, it's going to stay clear. It's not really how it works. And so looking at this gives us values for some standard materials. And you can see that your PDMS or your siloxane down there has a refractive index of 1.4. And you can see that it matches none of our clear products. And so if it is added in, you no longer have a clear product. So keep that in mind. And again, that's pretty similar for a lot of additives where it's not going to necessarily match the refractive index of the base polymer. So you're going to affect the clarity. So do keep that in mind. So what does that look like? Polycarbonate on the left, you can kind of see through it. Almost looks like it might be a little hazy, but you can still see through it, it's clear. And then you can see on the right-hand side, the polycarbonate now has silicone in it, the siloxane that has been added, and it is no longer clear. And so things to keep in mind. And then an additional note on here for additional properties is going to be your surface energy. So when we talk about surface energy, we think of things not wanting to interact with each other. So the lower the value, the less likely they want to interact with other materials, inks, or coatings. And so if you've ever tried to paint or to pad print on something like a propylene, you find that it's not so easy. And so generally you have to do some form of a treatment on it. So imagine that. Now we think the silicone is all the way down at a 21, so even further down than your propylene, and getting kind of close to PTFE or Teflon. So if you've got some non-stick Teflon cookware, you're aware that stuff doesn't want to stick to it. And so this is kind of your property that shows you that. So really low surface energy, stuff doesn't want to stick to it. So it allows it for the better COF and more of that silky feel. Okay, and then kind of how it works, as I mentioned, it ends up on the surface. And so it's already there, it doesn't have to migrate there, it ends up on the surface. So when it freezes off, cools off, is done being processed, it's at the surface to do its job. And that's what gives you your low COF because it's already there doing its job. The other thing to note here is using it different percentages will result in different functions. So less than 1%, It's going to be a little bit more of just a processing aid. So we're going to lower our pressures a little bit, maybe release from the mold a little bit easier, and that's about it. Anywhere for now from 1 to 10% though, we're going to start to affect the actual surface performance of the material. So we're low COF, affecting the touch and feel of it, and so that percentage. You do keep in mind different grades might also utilize different molecular weight silicone in them, which then might also dictate the amount you should be using. And so with any additive, always check and see the recommended usage and percentage and follow that for what you're trying to achieve. All right, so that was our slip agents, siloxane-based materials. Now we're going to talk for a couple slides on nucleating agents. Nucleating agents are used very commonly in propylene and nylon. So commonly, mostly in propylene that we note it, right? But you might not even know it's in there, and it's in there because it's helping. So nucleating agents, what it does is it helps to increase your crystallization temperature, your TC of your nylon or propylene. So during the processing cycle, when you are cooling the part down, it's in the mold now, it's cooling down, it's going through the cooling section of the cycle. What's happening is it comes down from its TM, or its melting temperature, which is when the crystals broke apart, you were able to flow it. Now we're cooling down, it hits what we call the TC, our crystallization temperature. Once it hits that, it starts to crystallize and form. And it continues to do so until you hit the glass transition temperature of the material. Your glass transition temperature refers to when the molecules can start to move. So as you might expect, if you go below its TG, molecules now no longer have enough thermal energy to continue to move. So all the crystallization is happening between your TC and your TG. And so if we can set it up sooner or increase your TC so it starts at a sooner time, it allows more of a range and more time within those two temperatures to allow for crystallization. And so that's kind of the function of your nucleating agent. So a common one for propylene is sodium benzoate, and you can also use other stuff. You can use minerals like your talcs, your colorants. They tend to have a nucleating effect on the material. But stuff like your standard commercial nucleating agents can move the TC up anywhere from 15 to 20 degrees Celsius. That's common. So instead of starting at like a 109 degrees C, which is common for propylene, it might jump it up to close to 130 degrees C. So as it's cooling down, it hits that 130 C, and then all the way down to its TG, it continues to crystallize. The other thing that I want to note here that I didn't necessarily put into writing is not only can the minerals, talc, kaolin, other things can also nucleate the material. So a carbon black can do it. And so if you're comparing a natural nylon or propylene to a nylon or propylene that's been made black with carbon black can have a nucleating effect on it as well. So you might see a little difference in maybe your shrinkage or your warpage between the two because of that nucleating effect that it has. The other thing to note, not only is it going to make it so you crystallize sooner, it makes it so it also crystallizes faster. Essentially what it's doing is it provides little sites for the crystallization to start to happen around. And so there's more of those sites now available. So what happens is it happens faster, and it creates smaller, more uniform crystal structures across all of those new sites that have been introduced by the nucleating agents. And so what happens with your more uniform crystal structures is you also end up shrinking a little bit less, because across the whole thing, there's a lot more sites to crystallize across more uniformly. So you end up with a little bit lower shrinkage. And so that's presented here comparing an unmodified 6,6, so no nucleating agent in it. It shrinks at 2% or 20 thou inch per inch, compared to basically the same material, basically the same 6,6, except for we've added in a bunch of nucleating agent to it. And so the shrinkage is now only 1.3 and 1.7. So it drops your shrinkage down as well. And so when we think about like the example I gave with carbon black, maybe your carbon black nylon shrunk a little less than the natural version. So things to keep in mind, we can add specific nucleating agents on purpose to get it to cycle faster and more uniformly, but also some things might have that effect even without it being distinctly a nucleating agent. So keep that in mind. And it's most common, we say most common in nylon and propylene, even more common in something like a nylon 6,6. because nylon 6,6 crystallizes faster already compared to a 6. And so adding the nucleating agent makes it crystallize even faster. And so common to see in that. Very common in propylene. A lot of the commodity grades that we sell, you're going to see that they come with a nucleating agent already. Okay. All right, and then the last couple slides, we're going to talk about chemical foaming agents. So again, kind of filtering through these a little quick, just enough information to maybe be a little dangerous. Again, if you do have questions or want more information on it, please feel free to reach out. We'd be happy to give more information, but just wanted to give a nice introduction to all these different additives. So chemical foaming agents, CFAs, they're used to eliminate sink marks, decrease weight, control warp. They can also provide thermal and acoustic insulation. So that's a nice advantage as well. So commonly they're used in maybe an area that's a little too thick. So we're starting to get a little bit of sink marks in that area. Maybe we'll use a chemical foaming agent to help with that. Do note that there's also, because these are chemical foaming agents, physical blowing agents also exist. But what happens is those are injected straight into the melt. They're not as common in terms of what we would sell. So CFAs, chemical foaming agents, are what we're referring to in these next two slides. But do note that a physical blowing agent does exist. So how it works specifically is your chemical foaming agent is going to degrade and it puts out a foam that then releases gases. So it creates those little cells, those little pockets of air. And so that pushes then the polymer out and up and kind of to take up more space. And so you don't end up with those sink marks. Or again, air lighter than your polymer, then it lightweights a little bit, creates the air pockets again that will help with your insulation. So any of those advantages are then achieved because of the cell structure it creates when the gas are given off. There's two different types of CFAs. So if you're looking at the additives, you'll see some that are noted as endothermic and some that are noted as exothermic. On the next slide, we'll kind of go through very briefly what that means. So again, chemical foaming agents, endothermic refers to any type of reaction, in this case with a CFA, when it's decomposing, that it's consuming energy, it's taking energy in. And so endothermic CFAs are going to consume energy when they're given off. They're typically based on bicarbonate or citric acid. Those are the common ingredients that are typically used for endothermic CFAs. Exothermic is going to be the opposite then. So instead of bringing energy in, it releases energy when it is decomposing. And so two different reactions depending on what you're looking for, and then different materials that they're commonly used in as well. CFAs also are typically not, so some of these additives can be compounded in. You'll commonly get a propylene compounded with the the nucleating agent, the color, what have you. It's not common for chemical foaming agents to be compounded into the material, because what we don't want to happen is when they go to compound it in, introducing that new additional heat history, we don't want it to start to decompose when you're just trying to make the compound. So these are specifically almost always just going to be separate that get added in after the fact, whereas some of the other additives can be compounded in already for you. So do keep that in mind. So some common materials they're going to use it in are going to be propylenes, ethylenes, different versions of PET or PET copolymers, so PETG, some soft touch materials, TPEs, TPUs, some polycarbonates, some ABSs, some nylons. So common in kind of your engineering to commodity based resins, it's pretty common. Not as common in something in your really high temperature range, your PPAs, PARAs, PEIs, sulfones. Really not common there, but more common in your more commodity engineering based resins. So great for weight reduction. In this case, you can see a big dash here. Might utilize it because it's a really large part. And so you might have issues where in some areas where it's a little thicker, maybe you had some sink issues, or maybe because we want to lightweight it because it's automotive, we want the best gas mileage. So we want everything to be lighter where it can be. Kind of a dual purpose there that you might use it in. Okay. All right, so our different additives. Now the last thing I want to go through, kind of a lot of words on here, but I do want to point them out. This is our things to consider page. So these additives have great function. So we want to add them in to do their job. We want to help nucleate it so we can cycle it faster, save some time on our cycling time. We want to add in our CFA to make sure we get good light weighting out of the part. We want to add the color so it looks great, or because we're making it for so-and-so end user that has a very specific color. But there are some things that we do need to consider. So great for improving potentially processing and final performance, but some limitations. So the first one is always going to be when you go to use an additive, if it's a master batch, meaning there's a carrier resin that has the additive in it that you're going to blend in, we want to make sure we're utilizing ones for the right resin. And so if you're using a polycarbonate, we want to make sure we use color or CFAs or whatever it may be that's meant to be used for polycarbonate. It's not so easy to jump across different uses because different materials will require different things. So always try to find or utilize a grade of additive that's meant specifically for that base resin. Some other things to keep in mind are high temperatures are going to be issues for things like your color or your CFAs. We might prematurely kind of start to decompose your CFA if you run it too hot. Maybe you put it in the dryer too hot. You might start to cause it to start to react, and that can be an issue. Thermal capabilities, some of them might already be on the fence with being able to utilize that color because that pigment might be right on the fence of that thermal capability for whatever you're processing. Nylon 6,6, polycarbonate temperature. So if you run it a little hotter, well, now you might start to degrade the pigment and now you're not getting the color you want. So we keep that in mind. And then also, as noted, you might be outside the limitation of the carrier resin if you're using a universal color. So also keep that in mind. Some materials have colors already that are different than your standard off-white or beige. So when you go to color it, we're already fighting some of a non-standard or what we would expect for a natural version of the material. So pictured here over there is a PPS material. You can see 3 different variants of color. And so the one on the far right is going to be kind of like your branched PPS. That's its natural color. It's very brown. Not only is it a high temperature material, it's very brown. So coloring it is hit with twofold issue. 1, we're fighting the brown. And 2, we're fighting that it has to be run at a high temperature. So certain pigments are not going to withstand the temperature needed. So things we have to consider. So if you come to us and you're like, hey, I want to run a PPS and I want it to be bright pink, our answer is going to be, that's probably not going to happen. But we'll see what we can do. Now you can color it. You can make them different colors enough that you can distinguish, hey, that's kind of some form of a blue, some form of a green. But again, we're kind of limited there. And then lastly, for this particular note, amorphous materials, they're not going to benefit from a nucleating agent. And so I would think that it would make sense, right? It doesn't crystallize, so it doesn't need a nucleating agent, but I figured I'd put it out there. So putting it in something else doesn't speed up an amorphous materials process because it doesn't crystallize. Okay, and then finally, the last few points are really just making sure we're not running things too hot. We're not trying to run them too fast. Maybe we're not drying them with the additive in it because it might be too high of a temperature. So just some things to keep in mind when we go to run them. You should also be receiving some processing information on these additives if you're going to be utilizing a master batch and adding it in. So there should be some information provided for processing it and ways and tips and tricks to make sure that you're successful when you process it. So again, lots of things to keep in mind, but these additives are super convenient and helpful in certain areas if you need those additives to improve whatever function or feature you need out of your polymer. Okay. And with that, that's what I had for you guys.
Great. Thank you, Andrea, again, for your comprehensive presentation. At this time, if you have any questions, please type them in the questions section or raise your hand and I will unmute your microphone. We have Jason Merkel, Technical Manager, on hand to assist Andrea with questions today. Excuse me, as a reminder, as you type your questions, please remember to complete the survey at the end of the webinar. Your responses will help shape future Chase the Knowledge webinars, and we always welcome your feedback. Also, please be sure to check out our webinars page at chaseplastics.com/webinars for past webinar recordings that you can watch at any time and future webinar announcements and registration. If you'd like to have a custom Chase the Knowledge topic presented to your organization, please reach out to Andrea or myself and we can help you get that set up. So questions, Jason, I'll turn it over to you.
Sounds good. Thanks, Sherry. Andrea, first question is regarding Delta E, back to the color side of things. Do you recommend a particular formula for Delta E, specifically referencing Delta E 76 versus 94 versus 2000?
That is a great question. I don't know enough about those equations to know what they utilize. And so the people or suppliers that do the color matching would know about those and would pick whichever one is going to be the best. I don't know them, and so I can't speak to that. But when a color match is done at a company that does, color and compounding in color, they would be able to answer that question.
Yeah, I can add a little bit here. I mean, it basically increases in complexity as the number value goes higher, right? Because I think that's based on the years that they were established. We do see Delta E76 used still relatively commonly in the plastics world, depending on the stringency of the color match trying to be obtained, with that being basically the square root of the each individual deltas compilation, right? So as we've increased to 94 and 2000, you see more advanced complexity, I guess, of the delta E calculation, accounting for differences in chroma and hue of colors, which aren't so readily read by the LAB calculations alone, the C-Lab. So it's a bit of a mixed bag. Arguably, if you can do Delta E2000, that would be preferred because it's going to give you the most holistic approach to color, although we don't see that as regularly employed across the polymer industry. So it's a bit of a mixed bag depending on who's making the color, how tight is the delta spec that we need to hit, and given the polymer at hand, can it even be controlled that tightly? So I know that answer is kind of gray, but we typically take that on a case-by-case basis and include, an end user's needs for, specific color tolerances in regard to how we move forward and what, color compounder or color house we may use to meet those requirements. All right, next question. Roughly how large of pockets do CFAs create, and do they tend to reduce tensile strength by creating, quote unquote, defects in the polymer?
As far as the size, I don't know that off the top of my head. They do report that, so we could find that for sure. And you might see some lowering of your properties a little bit. So it's kind of going to be one of those things where we find a nice balance between, is it okay that it lowers some of your properties a little bit, as long as it is helping with your sink or your light weighting, whatever you're trying to achieve by utilizing the CFAs.
Yeah, I think, depends on the polymer type that we're putting it into, depends on the type of CFA being used, whether it's exothermic versus endothermic. Are we putting it into a filled polymer, a rigid polymer, one that can be expanded easily? Say lower viscosity material, for example, will expand more readily than a higher viscosity material due to less resistance of the foam formation. So lower viscosity material might produce a larger cell size, if you will, in some cases. On averages, below 0.5 millimeter in diameter typically for cell size, but there is some variety to that depending on what we're putting it into. Thanks, Andrea. Next question is, can CFAs be used in vitro diagnostic cartridges without affecting the assays, i.e. do the chemicals leach or make a medical polymer no longer medical?
I think that comes down to wanting to utilize only materials that are good for medical applications. I'm not aware of any of these CFAs being recommended or to be used in medical applications because it could affect it. Now, granted, it is on the inside, right? But we want to make sure we're utilizing only materials that are really meant for the medical market. And I'm not aware of any of these CFAs that have been kind of made for that.
Yeah, I'm in the same boat. I haven't seen any medically approved CFAs either. Not to say that they don't exist, but maybe nothing that we've come across in our wandering so far. I believe that was the end of our questions. Great.
All right, awesome. Well, we would like to thank all of you for taking time out of your busy schedules today to attend this Chase to Knowledge webinar. As always, we hope it was informative and a great return on the investment of your time. If you have any technical questions that did not get answered today, feel free to reach out to Andrea directly. Her information is posted there on your screen. Thank you all for attending, and we hope to see you at our next Chase to Knowledge, and happy holidays.